Good evening and a warm March welcome to each of you. My name is Jenn Delamere and I am Director of the Geographic Information Network of Alaska, or GINA, at the University of Alaska Fairbanks. So what does this group GINA do? GINA is a direct broadcast satellite partner of NOAA's Joint Polar Satellite System, or JPSS program. In broad context, the purpose of this partnership is to deliver satellite data as quickly as possible to operational weather forecasters and hazard managers in areas of the world where observations are sparse. And yes, Alaska meets that criteria. Tonight, I join with my colleague Chris Waigl from the Alaska EPSCoR program to tell you about how wildland fire research and operations in Alaska benefit from satellite imagery. During the question and answer session, we will also be joined by Jenn Jenkins, a GIS specialist who uses these images in day-to-day operations at the Bureau of Land Management's Alaska Fire Service. When Chris and I decided who would open this talk, and I won the coin toss, I pondered for quite some time about the message I wanted to convey to you. And what kept repeating itself in my head was the age-old adage that every picture tells a story. The story of this picture, the Mackenzie River fire, will be told to you later in our program. And I'll open my segment tonight with a different picture, a beautiful image from my home state, Alaska. This October 2019 image was created at GINA using data from the VIERS instrument, flying aboard the Suomi NPP satellite. This picture has a special name. We call it Day, Land, Cloud. It's a handy composite image that helps discriminate water clouds from ice clouds and snow surfaces. Snow and ice appear as a cyan color, as do high ice clouds, while low-level water clouds are white. Funny thing, however, I chose this image not because of the clouds, because it was clear that day from south to north. And you can see remarkably that there's no sea ice along the north coast of Alaska in October. And what is the scale of this image? Well, I call it the huge scale. Alaska has a surface area of 670,000 square miles. 5% of its surface is covered by glaciers. 80% of active volcanoes within the United States are within its boundaries. The population of Dall sheep, moose, and caribou far exceed our people population of 730,000. And while we may have just over one person per square mile, it is the mission of state and federal agencies to protect people and structures in the event of wildland fire, near or far. And it is the mission of many University of Alaska scientists to study the impacts of intensified wildfire in the 21st century. What do fire managers and fire behavior analysts need to know about active fires? And how do they find the answers? Over the last 50 years, the tools of Alaska fire managers have used to chisel out these answers have changed markedly. As Randy Jant at the Alaska Fire Science Consortium recently wrote, and I quote, "Early wildfire detection in Alaska relied on keeping an eye on neighborhoods and on lightning storms. Much of the detection around the state was done by aerial patrols beginning in 1973. In 1978, the BLM had 12 aircraft dedicated solely to fire detection and another 6 smoke jumper aircraft, which often did loaded patrols after widespread thunderstorm activity. But by the turn of the century, yes, 20 years ago now, weather satellites were becoming the multi-tool in the toolbox. In 2021, in Alaska, we have largely transitioned to using instruments aboard 2 satellites for daily wildland fire detection and active fire extent, SNPP and NOAA 20, formerly called JPSS-1. These satellites are polar orbiters. They orbit the Earth every 100 minutes or so. With a swath width of 3,000 kilometers, they each complete 2 global pictures of Earth per day. But in Alaska, we don't have to wait for those daily images. Every time one of these satellites flies over Alaska, UAF GINA has 2 antennas on the ground to capture its data, and the computers on site to deliver and process the data for the Alaska Fire Service. Data from VIERS, the Visible Infrared Imaging Radiometer suite is used to calculate fire hotspots and create these incredible images at 375-meter resolution. The images are useful for obtaining active fire extent and examining burn scars. Turnaround time is important for wildland fire managers. We deliver these products within 20 minutes of the end of a satellite overpass. To that, add satellite Landsat and Sentinel products. Landsat and Sentinel are also polar orbiters. They also orbit every 100 minutes, but they don't see as much of the Earth at once. But what they do see, they see at incredibly high resolution, about 30 meters, perfect for precise fire perimeter mapping. For Alaska, Landsat and Sentinel images are available only every few days, so it's truly the partnership between frequent VIERS imagery and the precise Landsat and Sentinel images that have raised our game in this state. I'd just like to note that UAF GINA does not capture and process Landsat and Sentinel data. That's done by other agencies. And in some cases, manned and unmanned aircraft are available to fly over fires, as Chris will later discuss. So now that I've shown you sources of data obtained from space and aircrafts, just what do you do with it? What's our workflow? How do you get that data from space into the hands of fire managers? Well, we, the workflow, are talking to you tonight. Research, research to operations, and operations. Well, where do you start? Let's start with research. Chris Waigl, my co-presenter, is a researcher here at the University of Alaska Fairbanks. She works on many things, which you will soon hear about, but one thing she does is work on algorithms for VIERS, and she's recently come up with an algorithm to detect low-intensity fires. Work like hers going on around the country gets published in journals and shared at satellite science team meetings. There are then several groups in the country, of which UAF GINA is one, that contest whether those research-based products can be made operational. And I'm delivering this address to you tonight as GINA's representative. We use our direct broadcast data and our computer systems to put research in the development pipeline. And then we study the results, both with the researchers and eventually the operations folks. And if the research is ready to go to operations, we put it into our production pipeline and deliver it around the clock to colleagues like Jenn Jenkins at BLM's Alaska Fire Service. BLM, Alaska's Department of Natural Resources, and the USDA share management of Alaska's wildland fire operations as members of the Alaska Interagency Coordination Center. AICC has an incredible dashboard system to get information out to fire managers and to you, the public. So with that, I'll turn the mic over to Chris, and she'll take you through the stages of the Alaska fire season.
Good evening. I'm Chris Waigl. I'm a postdoc in the Boreal Fires component of the Alaska EPSCoR Fire and Ice project, where I work on imaging fire fuels and fire scars right now. I've also done my PhD here in Fairbanks and mostly worked on active fire, detecting it and pushing the envelope about what we can learn from imagery of active fire. I've known Jenn Jenkins from the Alaska Fire Service for many years and had many conversations about her use of remote sensing data and her need for certain kinds of products. And I have also used GINA data in my research, which is how I first met Waigl and Delamere. And this is how the three of us came together. What I want to do now is to take you on a journey through a fire season, guided by remotely sensed data and imagery. And what I would like to show you is how diverse and complex the use of satellite and aerial imagery is in managing a fire season, how interconnected the data workflow is. We are doing a kind of applied science here that relies centrally on the remotely sensed imagery. A fire season starts with what you see when you look out of the window. Snow. The end of the snowpack marks the beginning of the fire season. You have a nearly unbroken snow cover, which then about in April starts to get thinner. And I've pulled out an image here from a sensor called Midas. You will meet this sensor again a little later. And what we see here is an image of a snow cover index that goes from black, no snow, to these lavender tones, which means almost completely snow covered, going through those bluish colors on the way there. And I pulled out data from April last year, first half of April, when the first holes develop in the snowpack. And I would invite you to look where those holes are, because these are also the locations where we may first see fire activity. We don't only have Midas to get remotely sensed satellite-based imagery of snow cover as it goes away. This here is the animation of 4 years from 2016 to 2019 of the disappearance of the snowpack in Alaska and the Yukon. That comes from the imagery that the National Ice Center in the US distributes. This is also a satellite-based product, but it comes from multiple sensors, and they just publish the product. It's simpler than the Midas product in that it only has 4 classes: snow, ice, you can see the sea ice, open water, and the green is none of the above, meaning uncovered ground. The snow-off proceeds in very similarly the same rhythm, with some offsets. Sometimes one year is ahead of the others, but by May even, and especially June, they typically have caught up. Again, this will repeat quickly, and look again where the snowpack goes away first. Of course, we come down here from the west, but in western Alaska, and then often enough, you might also see the snowpack go away in the area of Delta Junction, which you probably know is quite windy. So there is often not a very thick snowpack in the first place. See here now, these areas in western Alaska are uncovered in 2016. 2018, it took a little longer. 2019, it was also quite ahead. The disappearance of the snowpack kicks off the production of fire weather indices. Here in Alaska, we get those from an organization called MesoWest. As soon as the snowpack is off, they start to calculate these indices that tell us how much fire danger do we have, how fire prone are we. This is one that is called Fire Weather Index, and it is plotted on a scale. If it's not much fire danger, it's blue, and goes to red if the fire danger is extreme. And I pulled out 2019 in late April. There you see again in western Alaska and around Delta Junction, which is here in the zoom-in area, we get actually quite high values of fire danger. 2019, if you were here in Alaska, you know this was a pretty intense fire year, and we will revisit the 2019 fires for the rest of the talk. What happened in Delta Junction in late April and early May 2019 was the Oregon Lakes fire broke out there. And this was very typical for an early season fire in that what you get after the snowpack disappears in these grassy areas is very dry, dead grass can burn in a very fast, what we call flashy fuels. And these images are from a pilot or from a plane that was sent out to monitor what's going on there. And May the 2nd, you see intense fire activity. You see what's called backing fire, meaning a fire progresses against the wind, creeping in the vegetation. And then 2 days later, there's still a lot of smoke going on. There's a lot of smoldering here, but you can see those burned grassy patches around those lakes, and that is the fire scar. Now, this was a fire service pilot, but from the perspective of the operational organization, what does our friend Jenn Jenkins at the Fire Service see? She needs to give out, she receives data and she gives out data to the incident command, to people who analyze fire behavior analysts, to fire behavior modelers if it's a bigger burn. So she needs more structured data. We need to move from imagery taken by a photograph to remote sensing data. And she gets 3 things pretty quickly after the fire starts, or almost immediately, in near real time for the first time, a little later for the third. The first she sees, and I attract your attention to this date here, the 30th of April, whereas the first was the 2nd of May. So the very first thing she sees are these fire detections, fire heat point. They may come from a sensor called Midas, from the sensor Midas that we saw earlier, that can also image snowpack. It may also come from a successor or a slightly newer version, similar sensor called VIERS on different satellites. VIERS and Midas are very compatible. VIERS has a slightly higher spatial resolution, so we like to use VIERS often. So she gets these fire heat points. She also gets in near real time, just the next day, she actually gets an image from VIERS. These 3 images here are all the same spatial resolution, the same map projection, the same scale. So you see that the VIERS sensor produces a relatively low resolution image, but this is still a very small fire. So they have determined where the start was from those heat points. And then a little later, Jenn will get a higher resolution satellite image. This is from a satellite called Sentinel, or a sensor called Sentinel, and has a resolution of about 20 meters. It's still burning here, so you can see the fire in this one too, and you can very precisely map the fire scar, which you could with slightly less precision here. So once you get this, for example, the planes are sent out and the other photographs are acquired. But where does she get those images from? How do they actually get to her? And this is where the science to operations organization comes in, and we are taking a break here and going back to Jenn Delamere, who will explain to us science to operations and what these words like direct broadcast mean and how we get those RGB images.
Pivoting back to the specific example of how wildland fire monitoring uses satellite products, I'm going to focus now on the VIERS instrument flying aboard 2 satellites, SNPP and NOAA-20. NOAA-20 leads SNPP by half an orbit, or about 50 minutes. With data received on GINA direct broadcast antennas, we see 16 to 18 VIERS views of some point on the north coast of Alaska per day, 10 to 14 views of central interior Alaska, and 6 to 8 views for southeast Alaska. The VIERS instrument itself has 22 spectral bands or channels from which to collect information. 5 I bands at 375 meter resolution, where I stands for imagery, 16 M bands at 750 meters spatial resolution, where M stands for moderate, and the incredible day-night band, a 750 meter spatial resolution, a nighttime visible channel. Yeah, it uses moonlight. It's pretty cool. This is a lot of data, and this is just one of many data streams available to the forecasting community and fire managers. So it is our job in research and research to operations community to boil this data down to something that can be quickly digested by a forecaster or a fire manager. For VIERS, we have recipes of channels that you can mix together to create an image that can tell you where clouds are or where the smoke is. These are known as RGBs, where RGB stands for red, green, blue. We reassign the VIERS wavelengths or channels to portions of the visible spectrum to make an RGB. One channel is assigned to red, one channel to green, and one channel to blue. As the number of channels on new satellites increase, so too must our product recipes. For wildland active fire monitoring, there are 4 RGBs that are particularly useful. Let's start with the one we can all relate to, called true color. This is a combination of spectral channels that best replicate what your eye sees, and it's a good way to find smoke. This image is from a NOAA 20 pass on August 19, 2019. The image has a lot going on over the state. The first thing you might notice is that there is a lot of white and gray over the ocean and land. These stark white patches are most definitely clouds. But what about the sort of gray, smudgy areas over the Chukchi Sea, over the Kenai? Smoke? Over the Kenai, a definitive yes, as you can see the smoke source, the Swan Lake fire. Smoke this thick definitely impacts air quality on the Kenai Peninsula and for Anchorage residents. North over the Chukchi, likely it's light smoke, but we'll be able to see if we look at a different image. Next up, the dayland cloud image is used heavily by weather forecasters and wildfire analysts. It has a different recipe, one designed to differentiate between water clouds, ice clouds, and snow. Notice again this patch over the Chukchi. We weren't sure if it was clouds or smoke in the true color image. But since you are largely seeing down to the water here, that's a good indication that it was smoke we were actually seeing in the true color image. The day land cloud image is also a great way to see burn scars on the land. Areas of bright green indicate active vegetation, whereas these brownish red patches underneath the smoke show us that the land has burned. And the eagle eyes amongst you will notice that there are other tiny speckles of brown. Those are mountaintops with exposed rock or dirt or dead vegetation. Okay, so where's the fire? I need to digress a moment to show you one very important single band that we use in assessing fires, the infrared 3.74 microns or I4 band. From this single band, we are able to detect fire points, and that serves as the basis for the next few images. One caveat I didn't mention, true color image and the day land cloud image, well, they're only available during the day because you have to have sun illuminating the scene for them to be active. But the I4 band, all on its own, can be used to detect fire at night, important for late summer fires in Alaska. Those pixels on the previous slide are directly translated into what we call fire hotspots or fire heat points. And they are really useful to fire managers. A hotspot or a heat point shows up on any image because we overlay it as a big red dot. And truth be told, analysis usually starts with the fire hotspots. Give credit where credit's due. These points are the bread and butter of finding active fires. But we aren't done yet. Moving beyond hotspots, we look at the day, land, cloud fire image. We changed just one item in our recipe to go from dayland cloud to dayland cloud fire. The R in the RGB is now the I4 band that I just showed you. Look at the difference. You can now see active fire burning. So this image is used for fire extent analysis. The blue component is also handy to see smoke during the day. Remember, each pixel is 375 meters in spatial extent. It's also important to note that if we have thick clouds, our fire will be obscured. Last but not least, we have an RGB we call fire temperature. Keep the 3.74 micron channel, but now pair it with channels in the shortwave and the near IR. At this point, you've got to shake your head out and reframe the color scale. First, we've changed the interpretation of water clouds and ice clouds. In the larger image, water clouds are now shades of blue and ice clouds are dark green. And more importantly, this new recipe now indicates fire intensity, a proxy for temperature, with red pixel colors indicating cooler fires, yellow for moderate intensity fires, and white for blazing hot at all three wavelengths. Burn scars are dark maroon. On this time lapse, you can see red and yellow and white and even green fold-over pixels on the western flank. This tells fire managers that this is a really hot portion of the fire. Head spinning yet from analyzing just one pass? Well, mine certainly is. So if you want to study these concepts in greater detail, go to a computer near you, look up these phrases on the web, or go to GINA's website. You'll see some excellent quick guides for reference. GINA's Puffin Feeder has current and archival imagery. Go to the Alaska Wildland Fire Information Series to see both fire hotspots, imagery, and loads of other info like lightning strike counts. But VIERS is only one part of the story. Remember way back when I mentioned Landsat and Sentinel and how amazing those images are for looking at fire perimeter? Landsat and Sentinel images are available online as well. So the question I put to you, if a picture is worth 10,000 words, what is an entire archive worth? And my answer to you is priceless. And with that, I'll turn this presentation back to Chris, and she will give you a continued imagery tour with lots more analysis.
Hello, me again. I'm glad to see you again. I'm back. You have now heard from Jenn Jenkins how direct broadcast works at GINA and what kind of products they're producing there, and and some overview about what you can see on the RGB products that are produced. And I want to just continue from there, right from there, and return to our previous journey through the fire season. We talked before about the early season fires. Now let's go to the intense phase, the typically highest intensity phase of the fire season, which typically starts sometime in late June and then goes into July, depending on what the weather does, if it's dry or if the rains increase the fuel moisture and then limit fire. So I want to go to a specific date that we will return to later, the 9th of July, 2019, intense fire season. And I have here a GINA produced true color RGB of Alaska. And you do need a little bit of experience to interpret these true color RGBs, because there is all sorts of white stuff going on. And some of this white stuff is clouds, a little bit is sea ice probably up here, and others is smoke. All this whole arc here is in fact a smoke plume. And the smoke comes from a variety of fires that burn in the interior of Alaska. This is where our other RGB combinations come in very useful. The Dayland Cloud RGB, you may remember it from Jenn's part, which uses part of an infrared band of the same sensor, which is VIERS here, is able to see somewhat through the smoke and the clouds. Not completely, the smoke is still there, but now it is more of a blue haze. You can also see some blue here, which is ice, either real ice or high clouds that have ice particles in them. Now the question is, we do not see any fires here, we only see the smoke. So how do we get to the fires? Well, in this case, to show you the usefulness of these RGBs for fires, I don't have one from the same day, but I have one from a very similar one from a different season. Here is a comparison of a true color RGB and the fire temperature RGB for a fire that happened in Canada. Again, the true color RGB is very much dominated by smoke. You can see that there's active burning going on here, but you cannot actually see the flames at all. Even if you zoom in, it's all smoke, no visible fire. But if you look at the RGB that combines higher wavelength infrared, suddenly the fire becomes very visible, and you can see that this intense area here shows up in bright red, and only the very tip here where the smoke is thickest becomes it stops being transparent to the eye. So from what happens actually is that this exact kind of data is also turned into those fire detections. The fire heat points that you see are nothing else but this very same kind of data transformed into pixel by pixel locations, into pixel locations that tell you there's fire there. So what happens here, how you interpret those curves here is this. At particular temperatures, radiation is emitted, and those lower curves here correspond to the temperatures that we have normally outside in the summer temperatures on the land. And those higher curves, especially this orange one, corresponds to the temperature of fire. And here are two of the infrared wavelengths that are used in detecting fire. One around 11 micrometer, one around 4 micrometer. And what you can see here is, if you look at normal background like this green area, you have only about 1/10 as much radiation in the 4 micrometer as here. This is a logarithmic scale, so each is a factor of 10 more. So only 1/10 of this, whereas up here in that fire area, it's the other way around. So the way you detect fire is to say, do I get a lot more in this wavelength and relatively a lesser portion in this wavelength? You get more radiation, but less than in 4 micrometer. This data can also be used to enhance the heat points. That's what we have done here. This is some work that we've been doing. Same day, July 9th. One thing that burned was the Shovel Creek fire up on Murphy Dome. You may have been there if you live in the Goldstream area. You probably attended some public information meetings, and we generated these images right there. This is this particular day, and what we've done here is to boost the fire detections, to also detect lower intensity fire that the standard heat point product cannot show. The orange ones are the lower intensity. And we also plotted them not as individual points, which sometimes I think are misleading because it looks like there's only this particular location that is burning. In reality, these are pixels like in an image, and they're pretty large. They're about a quarter by a quarter mile at a minimum. So plotting them out as the whole pixel footprint gets this entire area that was burning. And it was that big because that day the fire service conducted a burnout operation. So this entire line up here and over here was actually ignited by the fire service to burn out the unburned fuels and stop the fire from progressing further to the east. Another thing we can do with heat points is to tell stories. This was a long burning fire on the Kenai Peninsula the same year, the Swan Lake fire. What we've done here is to plot the heat points in color by day. So the purple points are the early fire, and then it goes over to green, and the latest where the fire was still burning in September are over here at the edge. So what this tells us is the story of the progression of the fire. It started up here, and then burned out over here all the way to the east and to the south. And then it got stopped here. Why was it stopped in a line like that? Well, fire service. This is the line that the Sterling Highway is along, and they stopped it at the Sterling Highway for a while. And then later, about here these days, so in late August, it jumped the highway in a few places and then burned down here and finally filled in the edges and a few of those valleys here. Another thing that you can see is these patches of spots that are green and were blue before. So what we can see is it burned early on in the fire, and then we did not have any detections here. And much later, like in late August, we got detections again. Now the fire was not out in between, and it was also not obscured by clouds all the time in between. What happens there is that the fire falls down below the detection threshold, and then when the weather conditions are so to reignite the fire, it can take off again. These are things that the fire service really wants to know, because knowing where there is still residual burning and therefore fire can take off again is of course tracking the hazard and monitoring the hazard. So much for the active fire. Now, what about fire before and after the fire? We also image fuels and look at burn scars. Looking at burn scars in analyzing burn scars is often easier than actually classifying and quantifying and mapping the fuels. So here's an example of the Stewart Creek fire in 2013. Two images of the burn scar. The Stewart Creek fire, I remember it well. I had to evacuate for it, and that was in July 2013. The left image is from July, the right is from September 2013. And I've used this image in classes and I typically ask the student, what are the differences that you can find between the two? And one thing that you can see is that in July, even though this looks not like an active fire, it still was. Look at this corner here. The corner here is filled in by burn scar, and here it was still not burned. So the fire still was burning along here, that the South Fork of the Chena River goes down here. Other things is that this here looks a lot more like a relief, whereas this looks really flat. The reason for this is in July, the sun is much higher. In September, it's already pretty low in the sky. The time these images are acquired is approximately the same, early afternoon. But the sun is already lower in the sky, so the relief is much more illuminated. The third thing is that you can already see how the regrowth has started, because this is very freshly burned. It's all in these brown colors, whereas here you get lots of green in between the brown. Similarly, from Jennifer Jenkins, I got these images between unburned and burnt vegetation. I think this is the Issam Creek fire, I believe. There's Dalton Highway is here. What you can also see sometimes is fire scars from previous years that show up because they are visible for quite a few years. Also, you can easily see those unburned patches. Not everything inside a fire scar burned. And as scientists, there is also research on how much actually is unburned and how much is unburned vary between different fire years, between different meteorological conditions, etc. And also precisely mapping the burned area is one of the main uses of these images. But what if we want to know more about the active fire, about the burned areas and about the fuels? We can turn to a different technique, which is called hyperspectral remote sensing. Hyperspectral remote sensing is different from all the other methods that you've seen up to now in that more spectral bands are available. You do not have just a few bands out of which you can have a handful of RGB combination. You have a whole spectrum, almost like looks like a continuous spectrum between low wavelength and the high wavelength. And different land covers will give you different spectra, and you can then distinguish them. We have actually a little movie here, which we made in the EPSCoR project. It was made by our visualization specialists, Cassidy and Naomi, and I would like to share it with you. It's, I think, the best explanation of hyperspectral remote sensing that is available. So let's go to our movie.
The Boreal Fires team with the Alaska EPSCoR Fire and Ice Project are using a technology called hyperspectral imaging to map wildfire fuels in the Alaska boreal forest. Images captured by a hyperspectral camera give researchers a unique ability to map the distribution, variability, and quantity of wildfire fuel types, which will be used to enable better wildfire management and prevention across Alaska.
To explain how researchers use hyperspectral cameras, let's first talk about sunlight and electromagnetic energy. Electromagnetic, or EM, energy radiates from the sun in waves of varying sizes. Most of these waves are not visible to the human eye, but they are still being absorbed or reflected by objects on Earth. The intensity of their reflectance can be measured by highly sensitive cameras through a process known as hyperspectral imaging.
A normal digital camera captures visible light waves reflected from objects in a scene and records this information in just 3 bands: red, green, and blue. The EM spectrum contains thousands of unique wavelengths, ranging from very large radio waves to ultra-small gamma waves. EM waves can be grouped into bands, like the red, green, and blue bands from our normal image, but rather than just red, green, and blue bands, a hyperspectral camera records hundreds of bands, representing a larger portion of the EM spectrum.
Researchers use hyperspectral cameras to measure and record EM energy. These cameras are often mounted on satellites or on airplanes to capture images of Earth's surface. Researchers are also gathering images from the ground to calibrate the airborne images, a process known as ground truthing. The higher a camera is from the ground, the more vegetation will be contained in each pixel. The closer it is to the ground, the more accurately it can identify the vegetation. Where a pixel from a satellite image represents a 30 by 30 meter space on the ground, and a pixel from an image captured from a high-altitude plane represents a 5 by 5 meter space. The Boreal Fires team is using a bush plane to collect hyperspectral images with pixels that will represent 1 by 1 meter spaces.
While an aerial image from a normal camera can tell us that a group of green pixels is a stand of trees, a hyperspectral image could help us determine what type of trees they are by identifying the tree's spectral signatures. Much like each person has their own unique signature, the chemical makeup of all materials can be accurately identified by the amount of EM energy they reflect, organized by wavelength and intensity. Our eyes register most plants as green because healthy vegetation reflects more energy in the green band of visible light than red or blue. In reality, vegetation reflects even more energy in near-infrared bands, making identification and classification of plant species easier and more accurate than relying on green visible light.
By using the spectral signatures of these plants, we can begin to map the boreal landscape. With higher resolution hyperspectral images comes greater accuracy in determining the types of vegetation present in each area. Once we have accurate maps of vegetation coverage, we can begin to predict seasonal wildfire risk and spread. Researchers will produce high-resolution maps that classify vegetation by forest type and will eventually extend this data to model for the entire Alaska boreal forest. Ultimately, hyperspectral imaging will help to develop science-based options for communities across Alaska to improve wildfire management and resilience. For more information on the Fire and Ice Project, visit www.alaska.edu/EPSCoR.
So now you know everything about our hyperspectral imaging in the EPSCoR project, which is my main job at the moment. And to conclude our presentation, this part of the presentation, I would like to go back and now take you back to our Shovel Creek Fire and Murphy Dome at the end of our 2019 fire season, and just go back and look at what kind of data do we have in the end for our fire to describe it. So here's the area where the fire burned. This is just the background that you would get, for example, on Google Earth. This is actually from Esri, company that makes ArcGIS. And this image was taken before the fire. The fire will be here. You can actually see an old fire scar over here. Now, looking at our Sentinel image, this is the new fire scar that was added in it. The old one, the new one. This was from May, so the blue stuff is a little bit of ice that was still there. Then we generated fire heat detections. This is now for a particular day. If I had all our data, it would cover the whole thing. But this was just one day, the day where it burned most. Now, for our hyperspectral analysis, what did we do here? Well, we looked at this area and we put some flight lines over it. Here's one flight line that our pilot flew with our camera. This is the image. 2, 3, 4, 5, 6. This is our flight lines. And we also went on the ground and did surveying of the fire scar. If you went to the graduate student talk, Christopher Smith was one of the field people here, the people who did field work here. You can see very well in this high resolution imagery that the fire scar is tracked with high precision, that the unburned vegetation inside the scar is tracked with high precision. You can also see unburned vegetation, unburned fuels outside the fire scar. You can zoom in and see those patches of, this is black spruce here, there's this deciduous here, which comes out in brighter colors. The purple tones are mostly the burned vegetation, but also bare soil shows up purple. This is actually from the side where there's the old fire scar here, the new fire scar along this trail here. We got magnificent high-resolution imagery of those unburned deciduous patches. The deciduous vegetation does not burn as readily. And we can actually do what we saw in the image. We can go here and look at black spruce, we can look at paper birch, and extract those spectra, and then continue our scientific analysis. We can then turn it into products. We can meet up with Jenn Jenkins and Jenn Delamere to see how the Fire Service can make use of this and how data can be packaged, productized, and distributed. And with this, I'm coming to the end of my part. I'm handing it back to Jenn Delamere to wrap it up. And then we all will meet in person. I will see you in a few minutes. And please start thinking about some questions you may ask. See you then. Thank you very much.
This is the part of the talk where I get to recognize the work of an incredible team of people. First, I encourage you to go back to the Science for Alaska archives. There are some great talks there that are directly relevant to what I'm speaking to you about today. Chris Smith, Denise Thorson, Randy Jant, Nettie LaBelle-Hamer, Eric Stevens. A great series of talks. You will not be sorry you went to look at them. We also have a long list of federal agencies that have contributed to our work at University of Alaska Fairbanks, including NOAA, NASA, and the National Science Foundation. We have an even longer list of academic partners, and it's at this juncture that I want to recognize a lot of individuals. Jenn Jenkins, Gary Schmunk, Willie Branson from the Alaska Fire Service, Allison York, Randy Jant, Robert Zeal at the Alaska Fire Science Consortium, Curtis Seaman at CIRA, Heidi Strader and Eric Stevens at the Alaska Interagency Coordination Center, our partners at Colorado State, our partners at University of Wisconsin-Madison, and most importantly, our UAFers, Martin Stufer, Uma Bhatt, Santosh Panda, Anushree Badola, Chris Smith, Jay Cable, Jeremiah Dabney, Carl Durking, Pete Hickman, and Greg Worth. So I've covered a lot of ground in this talk, but don't worry, you don't have to remember it all. If you'd like any additional information, please feel free to send an email to satellite@gina.alaska.edu and we can point you in the right direction. And with that, I will say thank you for attending and we look forward to chatting with you in the Q&A.
All right, that was a great presentation, Jen, Chris, and Jen. Learned a lot about that. And I know fires are such a big deal in Alaska, so I think that is all excellent information for people to know about how you all are working, largely out of view of the public to help fire agencies battle fires and to kind of assess fuels and maybe, that'll assist their prevention efforts going forward. So come on, folks, send in your questions there in the chat and through Facebook. I'm going to kick it off here. I jotted down a couple of questions, so I don't know who wants this one, Jen, or Chris, but it seems that there's so much going on in data gathering. So I wondered, how rapidly are things advancing in this realm? I mean, are we continually learning new ways of gathering data and using that data?
Thanks, Rod. I think that is a really good question for Jenn Delamere, who has, I think, the best overview about the upcoming satellite missions. There are a bunch of them.
Yes, in the next few years, there are more polar orbiting satellites being launched. In particular, there's another version of the JPSS satellites going that should be launched in 2022 or 2023. It will carry another VIERS instrument. So that's just going to be increasing our arsenal of data flow. And there are other European satellites as well as a few other national, international satellites that are going to be designed to look specifically at fires with particular sensors. And so while, every year you might get a new satellite or every year or two, there's an incredible workflow happening right now within our university partners, both in the UA system and around the country, to make our analysis of the incoming data more efficient and more productive for folks like Jenn Jenkins, our collaborator, who works every day studying this.
All right, we've got some questions coming in here. Here's one from Doug Loschbaugh. What's the relation between MODIS fire detection maps and the systems you have been discussing?
Go ahead, Chris.
Well, or you, any of us, or Jen. So MODIS, there are two MODIS. MODIS is the name of the instrument, and there are two of them on two different satellite platforms, both from NASA, called Aqua and Terra. The first MODIS went up in 1999, and the second in 2002. So they have been around for a while now, and in a way, so VIERS is a co-production between NOAA and NASA. So it's not exactly successor in the sense it's not exactly just a NASA satellite. But so from a practical point of view, the MODIS fire detections have a bigger footprint. They are at best a 1 by 1 kilometer pixel size. So you get them only every kilometer, which is about, let's say, how much is a kilometer? 1,000 yards. And so whereas the VIERS pixel size is about a 1/4 mile, so that's smaller. That's one thing. You also get typically more VIERS detections than MODIS detections for the same fire. So I've done some research on that, and depending on the year, you get about 2 to 3 times as many VIERS detections as you get MODIS detections. But I like to see them all in one big continuity. We can take this whole data set together, and it's good to have them all because the satellites only see the fires while they are passing over them, of course. And even though we are lucky up here in Alaska, because all those orbits, they converge towards close to the North Pole. So we get a few more overpasses than you would get in the lower 48 because, you know, they just all go together, get closer space, but you still only get 2 or 3 every afternoon from one instrument that might see the same fire. So there's still coverage gaps. You cannot really observe the fire with those polar satellites in continuity. You can with geostationary satellites, but then the resolution gets lower. This has been improving too, though. We have not talked about this in our talk. Jenn, any other remarks on VIERS versus MODIS versus others?
Well, I'll just say that MODIS and VIERS are both, we can receive those both in near real time, so they have a long history, which I'll ask Jenn. Oh, she's unmuted herself to speak a little more about.
Well, thank you. So I guess speaking from my perspective, I've been very pleased with how the VIERS heat detections and the images have been working for us here in Alaska. And as Chris said, the MODIS instruments are still in flight, but their viability is definitely decreasing. They have long outlived what anyone would have guessed. So from that perspective, what an incredible return for any investment there. But that said, we've largely transitioned to the VIERS platform because of the increased spatial resolution, and also it is kind of the replacement for MODIS, and so there's additional satellites that will be launched. So we're going to continue to build sort of this pool of data that we use.
All right, we've got other questions in here. Jonathan Rivera wants to know, and this is timely because we're into March here, so summer's coming around. Is it too early to assess the probability of wildfires this year? So y'all have the answer for that? You got everything figured out for us?
What I can tell you is that Predictive Services on March 1st came out with their forecast, and it is early, but at least for Alaska, it's looking like a typical fire season. Now, typical is kind of a deceptive term, but it's not showing up as, at least at this point, not being predicted to be extreme.
Okay. There are a couple of things on here about lightning. Where does that fit in? I mean, do you all detect lightning?
We do. The Alaska Fire Service owns and operates its own lightning detection system, and that information comes into the Alaska Fire Service, and it's then distributed in several formats. But lightning is an important component to wildland fire here, in that it's, as our poll questions suggested, it's a major source of ignition, and so we definitely want to keep an eye on where we've had a concentration of lightning strikes, especially if you have a concentration of lightning strikes in an area that looks like it has extreme fire weather indices.
Okay. Here's another lightning question here, and it's from Aisha Yeager. I hope I'm pronouncing her first name there correctly. And this has an acronym in it that I have no idea what it is. So are the lightning maps / data also working in coordination with the WWLLN by any chance? Just wondering. Do we know what that acronym is?
The Worldwide Lightning Location Network.
Ah.
Certain, I'm not, we do make the lightning data, it is available to the public, so it may be incorporated in that. I'm not sure.
Okay.
I'm also not so sure. I don't work too much with the lightning data, but others in our project have, and I do know that it's the sensors are sort of, they have a spatial area that they cover. I'm not completely familiar how they are all networked together.
Okay.
But what we also use is the same data that Jennifer Jenkins is organizing.
All right. Well, let's go on with another one here. Lightning seems to be kind of an issue here tonight. Do you have, this is a question from Barbara Solarius. Do you have data on lightning going back in time that would let us know if lightning is increasing, whether statewide or in particular locations?
We do have lightning that goes back quite a ways. It gets a little tricky looking at trends with lightning because at least for the data that I have access to through the Alaska Fire Service, they changed instruments sort of, I think it was in 2012. And so the way that the systems recorded lightning is different. Now, the comparisons could certainly be made. And if my memory is correct, I believe that, Chris has put up a lightning, a link to a paper that speaks to these trends. So thanks for that, Chris.
Okay.
Yeah, I switched off the camera because I have the feeling that my internet connection, unfortunately, is getting a bit unstable. But in our project, Peter Bieniek and others have written a paper about lightning trends integrating several of the sensors. There was a sensor network was replaced by another, and there's needed work to be done to make the different time series compatible. If you change how you measure lightning, you will obviously get different results. So you have to do that. And so that is a place to look at this link I put in the chat. The paper is called Lightning Variability in Dynamically Downscaled Simulations of Alaska's Present and Future Summer Climate. And that is in particular also with the idea of lightning as a source of fire ignitions.
You know, I had a question as I was listening here. You know, it sounds like you can almost do anything here, but what are some of the limitations and challenges you have, especially in a busy fire season?
Well, I would speak to I think the biggest challenge that we face with this, getting this remote sense data to folks that can use it in the field is finding a data format that is easy to use and that you don't have to be a GIS specialist to use. And so when I saw in the chat, the questions came up about, statewide imagery for smoke distribution for aviation purposes. I think, with my experience in using the VIERS images, I immediately thought, well, yeah, I bet we could do that. But that first step is getting this information in an easily consumed format. And it can be overwhelming, right? So as we continue to layer, information from satellites, different satellites, and, the picture becomes pretty clouded and can be a little overwhelming. But I think that's, but one of the big things I focus on is trying to streamline that distribution of information to really lower that overhead so that it can be used by a wide variety of users.
And does that include prevention? Do local governments or state agencies use this for fire prevention in any way? Doing fire breaks, is there that kind of a use?
Absolutely. With the as we get better and better fuel maps, that'll help that'll help fuels planning on a large scale. Like you can do fuels planning on a local scale, right? Because you can walk outside and you can see what's out there. But sort of these larger, broader projects, an increased, a better field map, just a better sense of really what the vegetation is on the ground is a really big step.
Okay. We've got a question here from John Pace, and we're going to start winding down here, I think, soon. So if anybody has questions, be sure to get them in soon. John asks, is there an estimate for how much money is saved by using satellite data instead of flying airplanes to monitor fires?
That is a tough number to get a handle on, because it's not just the cost of just the aircraft costs, but when one starts to figure in risks and putting people in risk avoidance and such, that equation gets kind of murky. What I can tell you is that with one of these VIERS passes, we can remotely monitor fires across the landscape, which would take several hours of flight. But trying to tackle that number, or trying to wrangle that number in, is something that there's been a number of us who have really sort of scratched our heads about, and we haven't come up with a very good answer yet.
Okay.
Well, and I can't speak to the cost, but I would say that we found, well, thankfully 2020 was not a heavy fire season, but satellite imagery was going to be incredibly important during the COVID pandemic as well, because there wasn't going to be the capability to fly the same way you could pre-COVID. So it was using that satellite imagery is very important in extenuating circumstances like we just had as well, or are having.
All right, we've got a couple more questions that have come in here. This is from Joyanne Hamilton. She asks, do you work with agencies when folks decide when and where to send firefighters? She says she saw a map once that showed areas of Alaska based on population, in which areas are prioritized over other areas. So do you connect with other agencies on such planning?
Work like that those planning efforts take place at a higher level. So it's at the Alaska Interagency Coordination Center. That's one level where that planning takes place. Now, in the case of a really big fire year, they will come together. Members of the Alaska Interagency Coordination Center, the representatives, will come together and have daily meetings and review, look at what fires, what the fire activity has been, what the weather forecast is. And so, wildfire, the wildfire community in Alaska really is interagency, as is in the lower 48.
I wonder, where would we be without satellites and all this data collection? We'd be in a world of hurt, do you think?
I think that we're really we've been very fortunate that we've had these technologies and the ability to consume these technologies. They've kind of converged. It's been kind of this, just a really great mix of, maybe it's just luck. Mm-hmm. But I think where we, at least for how I view my position and what I view as being important for the job that I do, the past 5 years have been, we've seen a really big shift in how we approach some of these things, and it's been because we have access. It's because we have access to this imagery in a format that we can consume.
One other question here. Where did it go? Doug wants to know what percentage of interior Alaska has burned in the last 25 years. Do we know that?
So I put some information in here into the chat, including a screenshot. The last 25 years, now, of course, you give us one particular date. Had you said 30 years, had you said 50 years, it would be different. But there is a picture of the fire burns since the 1940s when we have data, and it is between the Brooks Range and the Alaska Range, which is the bulk of the Alaska boreal forest. it is not insignificant. It is a pretty good amount of it, put it like that. To have real numbers, you would have to ask exactly very precise questions. Do you only want the forest, or do you also include mountains? Do you include built-up areas, etc.? Do you include high-lying or low-lying riverbeds or something? So you come up with different questions depending on how exactly you measure. But I put the link into the Alaska Fire Science Consortium's brochure called Alaska's Changing Wildfire Environment, and it's very readable and has pictures, and you can get good visual insight into the statistics that have to do with fire. Also, Randy Jan's talk ago, which is more geared towards wildfire and climate change, and the interaction between the two is a great one to check out from the YouTube library of past Alaska Science for Alaska talks.
All right. I think we're going to wrap it up here. So, you know, for any of you there, do you have any last kind of comments you want to say here about, you know, about data collection, about the work you do, and maybe about the fire season ahead? Who wants to go?
Well, I'll just say I am very pleased to work with Chris and Jen, and the Alaska community is incredible. So I look forward every day to my interactions with such great colleagues, and I think we're unique here in Alaska in our ability to work between agencies, and the interplay between the University of Alaska and our federal and state partners is incredible. So I'm grateful for that, and look forward to our incredible partnership moving ahead.
All right.
I would just like to say that it is, I think, really important to do this kind of work in the partnerships that both Jen's kept mentioning, because you need to have users to ask the right questions. And a little thing that Jenn Jenkins said earlier about getting the satellite data in a form that the fire service, for example, can use it is also important. Often enough, researchers just produce something, find out something, say, oh, if we do it like that, then we can get this result. But that doesn't put satellite imagery in the hand of the user. You really have to line up all the steps to actually make the systems compatible. When you produce something, how you produce something, what data formats you use. It's a lot of very detailed work that also needs to be done. And I think personally that it is part of what a researcher should be interested in.
Jen, how about you? Any final thoughts here about working with these folks in the season ahead?
Well, I'm certainly grateful for the opportunity to share some of this information about sort of I guess give folks a little bit of an insight into what it is I do on a daily basis, and I'm fortunate that folks are interested, and again, it is the Alaska wildland fire community is welcoming, and it does seem like a very unique group of individuals who are coming together for common goals, and it's nice to be a part of that.
All right, well, that's going to do it for this presentation, which was excellent. Thank you all. As somebody who lives in fire country, and like Chris I wasn't evacuated for that fire, but it was getting close and we were loaded up and ready to go. So I know the importance of all this information. So thank you all for presenting that. It was a great time. And that wraps up not only your presentation, but it wraps up the season here for the Science for Alaskans series. It concludes the 29th season now. And I hope you all come back for the 30th one next year. You can find this presentation and all of this year's presentations on the Geophysical Institute's website, Facebook page, and YouTube channel. And as I said earlier, you can find any of the talks going back to 2009 on our website. So thank you again. Hope everybody has learned a lot, well informed, and looking forward to next year. So thank you all very much. Good night, and we'll
Thank you, everyone.
Good night. Thank you.
Night.